Okay, so basic cardiac physiology. There's a lot of topics here. So we're going to start with cardiac output. So first of all, what is cardiac output? We're going to abbreviate as CO. Cardiac output is the volume of blood that is pumped out of the heart per unit time. And the way we calculate this is we look at stroke volume, which is the amount of blood that the heart kicks out in one heartbeat, and you multiply that by heart rate. So that's the amount of times the heart beats per minute. And that gives you cardiac output. Now this is a definition of cardiac output, but the way we can actually measure cardiac output is we use fixed principle. And fixed principle is that cardiac output equals to O2 consumption over the difference between the arterial oxygen saturation minus the venous oxygen saturation. And I'm going to explain how we got this. Basically, the underlying principle is that the amount of oxygen we consume is equal to the difference in the total oxygen content in the arteries and the total oxygen content in the veins. So the way we calculate the total oxygen content in the arteries is cardiac output times arterial O2. Okay, so that's like a volume of blood times the amount of oxygen in the blood. And you subtract it from against cardiac output times venous O2. Okay, so that's the basic underlying, relation behind the Fick principle. So once you understand this relation, it's very easy. You just isolate cardiac output, and then you can get the usable Fick principle. So we isolate cardiac output. And then we're going to isolate it again. And now this is, voila, that is the Fick principle. And basically you can get this number and this number from you can stick catheters up and they'll tell you the oxygen content. One thing to note is sometimes you can get the venous content from the pulmonary artery, so that's kind of confusing. But remember that the veins will drain into the right heart, which will pump into the pulmonary arteries. So it's all the same oxygen content. Alright, so next we're going to take a quick look at stroke volume, which I've already mentioned. Remember, that is the volume of blood ejected with one heart contraction. And the way the equation we can use for this is it's end diastolic volume minus end systolic volume. So end diastolic volume is the volume of blood that is in the heart at the end of diastole, actually, which is after has finished filling up. And the end of systolic volume is the volume of blood in the ventricles after it has fully contracted. So that's at the end of systole. Now, the end diastolic volume is basically determined as preload. So that is one way that we affect stroke volume. There's a couple other ways to affect stroke volume. One is contractility. So if you have a better contractility, that means your heart can squeeze better, so it can squeeze more out, so you have a higher stroke volume. And lastly, we have afterload. Afterload is basically the aortic pressure. It's the pressure that the heart has to pump against that is resisting the heart from pumping. So higher afterload means a lower stroke volume because there's higher resistance to pumping out of blood. Now preload, we said, was preload is dependent on venous return. So if you have less venous return, then you will have decreased preload. So if you give a venous vasodilator such as nitroglycerin, you're going to increase the venous capacitance, and so more blood is just going to hang out in the veins, and there's going to be less venous return. And if you get less venous return, thus your preload decreases. Now afterload, we already talked about that. So next thing is called ejection fraction. That's the final concept we want to talk about here. Ejection fraction is defined as the fraction of the blood in the left ventricle that is pumped out in each stroke volume. So it's basically in each stroke volume, the fraction of blood So the total amount of blood in the ventricle before the stroke is called the EDV, and diastolic volume. So that is our equation. Ejection fraction is the fraction between stroke volume over and diastolic volume. And so this is index of heart contractility. Because if you have better contractility, you're going to get better ejection fractions. All right, so that's it for our cardiac output.